Okay, today we have Jin with us. He's Kapil's advisor. Unfortunately, Kapil cannot be here, so I'm hosting over here. And he's visiting from Northeastern University in Boston. So he's going to be talking to us about checkpointing and the work that he's been doing the last few years. So, please.
Thank you. Yes, and thank you very much for inviting me. So the title here is Checkpointing the Un-checkpointable. So basically, if we've been working in this field of checkpointing for about 15 years or so. So if you have heard me give this talk, if you have not heard me give this talk before, then this is a good time to break in. If you have heard me give a talk on checkpointing before, then please forget whatever I told you before. Because now I think we finally know the right way to do checkpointing. And so this is what I'm going to try to explain. So that's why the title, Checkpointing the Un-checkpointable. And then as part of the story, I'm going to talk actually about 3 different strands that come together in maybe an interesting way. One is the checkpointing itself. Another is the split process approach. And then the third is formal verification. So, okay, so at this point, you can see an outline of the talk. First, I'll review our software DMTCP. Don't worry about what it stands for. Never let a student name a project. But in any case, I'll give you a short introduction to it and even a very brief introduction to our plugins. It's our plugins which extend the power of the checkpointing in an intrinsic way that other kinds of checkpointing packages just do not support. That will become clearer when I talk about that. But then finally I get to the interesting part, split processes. And this is the totally new approach, very different from whatever we've done before. Let's see, after that, of course, since I'm here at Microsoft, I especially wanted to talk about the challenge of Microsoft Windows. Because Microsoft Windows by design has a design that can be more efficient because the information about processes is shared between the kernel and user space. But for checkpointing, this makes things especially hard because normally we would just say copy all of the user space memory and you're done. But if some of that user space memory is intimately tied with information about this process, and this process will not exist in the future, we have a problem. In any case, after that interim, I want to move on then to talk about formal verification. And here, formal verification is the third strand here, and I want to show you that at this point there's some interesting possibilities for doing a certain kind of debugging which would have been very difficult in the past. And that's maybe the proof that what we're doing is new and interesting. And then just a few words at the end. So, a review. So we've been at this for about 15 years. The typical use case was high-performance computing, but not in the way that most people think about it. People say, okay, you're going to have 200 computer nodes. One node could crash at any time. We better checkpoint, so if it crashes, we can fall back to it. But in practice, at least from what I see, that's not really the most common application of checkpointing. The most common application is we have a job that needs to run for a week, in this case 18 hours, and the batch system has a maximum allocation that they can give you for obvious purposes. The systems administrator would go crazy otherwise. So if the maximum allocation is 12 hours and you have an 18-hour job, you have a problem. But with checkpointing, it's not a problem. You checkpoint before the end of the allocation and then restart in the next allocation. We actually started at the low end, not at the high end. At the high end in supercomputing, they've got lots of resources and they prefer to carefully do their own application-specific checkpointing. But at the low end, there were many people who had long-running jobs and they really worried, often even if it's just their desktop computer crashing because somebody turns out the power at night. So it's meant to be very simple. Here we see that we can do the launch. In this launch, imagine the launch isn't there and you see a command line. So the idea is you just use the command line with DMTCP launch as a prefix. Then when you're ready, you can give the checkpoint command. There are several ways of asking for a checkpoint. The program itself can have an embedded request to do checkpointing. You could request periodic checkpointing. Finally, you'll restart. Every process that's been checkpointed will be written out into a separate DMTCP file. We support distributed and parallel computing, so those might be on several different hosts. If those checkpoint files are on several different hosts, it's okay. We also write out a restart script, which will then proceed to call restart on each of those on the correct host and join them up. So let's look at the basic architecture. So we have a centralized coordinator because from the beginning, we always wanted to support distributed computing. And how does this work? Well, recall that we were going to do DMTCP launch. What launch is going to do is inside it's going to set up this environment variable LD preload, and I'll set that to our checkpointing library. So now our checkpointing library will have a global static constructor, so that will take control before the user's main routine. So we get control first. Perhaps we're over there on the left, process 1. At that point, we go looking for the standard location of the coordinator, or if not, we'll create our own. And then we'll also create our own checkpoint thread. And now there's a third thing that we'll do. So we connect to the coordinator or create a new one if we need it. We create a separate checkpoint thread, which mostly will stay quiet and do nothing to not interfere. But later at the time of checkpoint, it will come alive and it will pause the user threads. So we need to pause the user threads. The way we do that is we set up a signal handler. In this example, it's SIGUSER2. And so now with that signal handler, when it's time to checkpoint, the coordinator sends a checkpoint message down to every process. Each process then causes the checkpoint thread to wake up and to send a signal to each of the user threads. The user threads now go to our signal handler since we're the ones who declared it. And of course, a signal handler is process-wide. It's not per thread. And now they immediately go into a semaphore and they don't do anything until we let them. So at that point, you can more or less guess how we can do the checkpointing. We just copy out all of the user space memory to this DMTCP file, and we're mostly done. There's still 2 more wrinkles to tell the whole story. The first of these 2 wrinkles is that there are various kernel constructs that we might worry about. Maybe there are open files. Maybe those open files have a file offset. But there are standard system calls by which we can discover all of this. So we'll actually interrogate the kernel about a lot of its constructs and put that in the user space memory before we save everything. And then the second and last wrinkle is that this might have been a distributed computation. Distributed or parallel, we don't really know the difference. For us, a parallel computation is distributed. MPI is just an unusual distributed application. So, and we make sure that our checkpointing library is more or less sticky. If you call SSH to create a remote process, there will be a library attached to that one too. But now, before we checkpoint, there could be some data in flight in that socket between the 2 processes. If it's TCP, then the solution is fairly easy. We have a cookie, let's say, a roughly unique set of bits. It's random, but if it's large enough, it should be unique. And everybody sends this cookie down through the socket, and then in the next phase, everybody receives until they see that cookie. Then there's no more data in flight. And now, finally, again, we can save all of user space memory, and we're good. And of course, restart is just do everything in the opposite order. If it's InfiniBand, there's a student who got a thesis out of that, but we also support InfiniBand. When we support InfiniBand, there it's harder because there is InfiniBand hardware, an HCA adapter. and you can't really save the state of hardware. And there will be a software library that's talking to that hardware. So what we have to do then is we create, that software library has a struct that refers to the hardware. That struct even has hidden fields that are not documented at all and could be different in different implementations. So then we create a shadow struct. And we make sure that anybody who wants to talk to the HCA adapter has to go through our shadow struct first. And then we just copy information over to the real HCA hardware adapter and its struct. And then on restart, we do the obvious thing. We'll start a new HCA connection with HCA, and then we'll create a shadow struct that reflects that actual struct used by the hardware. So it works for TCP. It works for InfiniBand. That's great. It does not work for something like Cray GNI. It does not work for, say, Intel Omnipath. And probably it's not going to work for some of the newer networks. And I can't afford to assign a new PhD student to every single new network that happens to get invented. So this is one part of the problem that we're facing. So when we look at checkpointing in our team, there's one fundamental question that really has been driving me for these entire 15 years. For me, I just find it fascinating. That's me. But in any case, what are the limits of checkpointing applications in the real world? So we can save now pretty much all of the various kernel constructs. We can handle TCP, we can handle InfiniBand, but my God, now they're using GPUs. How do you save the state of a GPU? That's hardware. So there are problems there, and we'll get on to that. In fact, there was a very strong group in Japan that was checkpointing CUDA for GPUs in CUDA version 1 and version 2. And then in CUDA version 4, they stopped. They stopped because that's when NVIDIA introduced uniform address spaces. So a single address either refers to an address on the kernel or on the host, but it's unique because there's a uniform address space across device and host. And at that point, the CUDA library was no longer restartable, and apparently that broke their approach. So at this point, we're probably the only ones who can actually checkpoint CUDA through a related technique, and we'll come to that. Second, let's see, this is definitely scalable. We've done experiments, for example, at TAC at the University of Texas at Austin, where we take real-world software and have even run over 32,000 cores, and it works. I think in the worst case, it took us 11 minutes to do a checkpoint. But at that scale, maybe that's okay. And there, the bottleneck really was the time to write to disk. So now that we're moving to SSDs, even that time would be much less. But the real moral of this talk is I want to bring together 3 different strands. So we've talked about checkpointing. Next, I'm going to talk about split processes. And then in the last third of the talk, I'm going to talk about SimGrid and its support for a certain kind of formal verification based on model checking. So, and then what I want to claim is we have checkpointing plus split processes plus SimGrid, and this changes everything. And that's why I said, if you've heard me talk before, forget whatever I said. We finally know the right way to do it. I won't stop to read the advantages, but basically we think that this really makes us much more flexible. There are things that we could never do before on several fronts, and now one solution seems to solve those several fronts. So before going into details, let me just give you the basic idea, a split process in a single slide. So at that point, you'll understand 2/3 of the talk. We only have 1/3 to go after that. So here's the idea of a split process. Imagine that this is the address space and that somehow we can tag all of memory. So it's associated either with the upper half or the lower half. You can imagine the upper half meaning the higher part of the software stack. Also, it's by analogy with device drivers where they also talk about upper half and lower half. But whichever way you think about it, we have somehow managed to split all of memory into upper half memory and lower half memory. And the way we're going to do this, in fact, is we're going to start 2 independent programs in two independent processes. And then we're going to take those two independent processes and we're going to smush them together into a single process with a single thread of control running both. And the flow of control can go from one to the other and back again. And it's going to be the upper half, the MPI application, of course, which is controlling everything. And it will make calls downstairs to the MPI library as needed. So I won't go into the technical details, but let's start to think about if this is possible technically. And afterwards, I'm happy to discuss why it's now possible. Then what are the advantages? What do we gain from this? Well, remember I said that I was always worrying about what are the limits of what we can checkpoint. And in the earliest days, well, okay, so you have a job running on a CPU, and if we can checkpoint a CPU-intensive job, then we're done, because everything else involves hardware. We can't checkpoint the network. We had the slogan, you cannot checkpoint the world. And we needed to draw a line between us and the world. This allows us to draw a line between us and the world. Everything below that line is for the rest of the world. So the idea here is that MPI library also is talking to its own network library, whatever it prefers. If it's going to use Intel Omnipath, that's okay. We're not going to support that. They are. And now, when it's time to checkpoint, since we've tagged all of memory as upper half or lower half, we're just going to checkpoint the upper half memory, and that's it. So our DMTCP file is only the upper half. So we've done the plumbing already. When the MPI application tries to call MPI, we're going to use a trampoline and point it into the lower half where the actual MPI library or the active MPI library is. And that active MPI library will talk to the network hardware and make everything happen the right way. Now we save the upper half as a DMTCP file, and now it's time to restart. So how do we restart? Well, the good thing is that lower half program is completely independent of the application. So in that lower half program, we're just going to start a new trivial application, which will be an MPI application, but it's running some trivial program. And that trivial program has two very simple jobs, and then it can go out of business. Job number one of that trivial program in the lower half, so we started running across the entire network. Each core perhaps has its own MPI rank. And job number one is we need to go through the MPI library, and for each of the functions in the API for MPI, we need to create a vector or an array of addresses, one for each of those entry points into the MPI library. And then once we have this array, we're now going to pass control back up to the MPI application we're going to copy into upper half memory the checkpointed file. So now the upper half will finally exist. It didn't exist yet. Initially we had just the lower half trivial program running. We copy the upper half. It looks exactly alike, bit for bit. And we pass into it a pointer to our lower half array that has all the MPI pointers. And now the MPI application upstairs is going to call a special restart routine, which will then proceed to create a trampoline from the normal MPI location on the top down through that array on the bottom to the correct location of the lower half MPI library. And now we're all connected. And after this, we can do exactly the normal restart that we would always do. After that, there's no difference. So that's split processes. And so what's kind of magic about this is MPI, so it's running across many hosts and many cores. But we don't need to know anything about that. On the bottom, for example, the trivial application is going to start the trivial MPI application. Each MPI rank is going to ask, what is my rank? Then it will go looking for the DMTCP file that corresponds to that rank. And it will then load up in the upper half the upper half memory from exactly the same rank. So it's perfectly matched. And after that, we're back to the single process case. Good. So let's say a little now about plugins. So these are plugins in exactly the same sense that browsers have plugins, so that you can extend their capability. Plugins was the earlier idea, and that was going to be our solution for how to get beyond this limitation of hardware. If there is a session talking to the hardware, database, network, whatever, we just need to create a semantically equivalent session at the time of restart. So again, that was our first solution about how we're going to talk to the rest of the world. A key idea as part of the plugins is something that we call process virtualization. So the simplest example is here. So if you have a friend who happens to have their own checkpointing package, and you're curious how your friend is doing the checkpointing, you can find out with just a single question. Just ask them, how do they handle process IDs? Because on restart, you might be on a different host, a whole new kernel. The old PID, maybe somebody else is using it now. Maybe it's no longer available. So there have been some solutions where there will be a kernel module which will modify the kernel table itself. Another one, many people have heard of this, is a package called CREU, which is used especially in the single host case. And in the case of CREU, they can also basically hope that the process ID is still available in the new destination kernel, or else they'll run under a container. And if they run under a Linux container, then again, all process IDs are available and they create everything. But that has its own cost, because a container, by design, has isolation with the rest of the world. And so sometimes you want to restart, and maybe you don't want isolation with the rest of the world. Maybe you want to continue talking. And in CREU, they can continue talking with the rest of the world. There are various bridges, but they have to make that extra effort. It doesn't come immediately. So how do we do it? Yeah, question.
So who is using the process IDs? Is it the user application? Is it the MPI library?
No, the user application.
And why?
Good, and that's exactly what I'm about to describe now.
Okay.
So in this case, we're not back to MPI yet. This is just two processes that talk to each other, and we want to save their state and later restore it. So when these processes start up, if a user process calls getPID to get the process ID, the kernel will pass in the actual process ID, 2652. But we have a library in the middle here, represented here by this translation table. And in that translation table, we will mark a virtual process ID 4000 as the process ID that will be known to the user. So the user copies in 4000. They store it somewhere in their memory. We have no idea where. It would be very difficult because they could store it several times. They could pass it to the other process. So the rule here is never let a user know what their real process ID is. And similarly with kill, we're using kill as an example because now we have the two processes talk to each other. But I think from here you can see the idea. We call kill on 4001. Before it gets executed by the kernel, it goes through our library. Our library translates 4001 to 3120, and the kernel sends the signal through to process ID 3120, which happens to have virtual ID 4001. And then on restart, I guess it's obvious what you can do. When it's time to restart, we'll take control before we allow the application to continue. And at the time of restart, we will update this translation table, this library. So each process will ask the kernel through our library, what is my real process ID now? And then we update that table, and then we continue executing. So this works fine for process IDs, but essentially it works very well across a huge number of cases. You could even think of our InfiniBand solution as a general form of exactly this. So a lot of our plugins are using this kind of virtualization, which we're calling process virtualization. And then finally, just to talk about the power of this kind of method, there's this really nice example here from Intel. So we've been working with Intel for more than 5 years. They've been funding us. In fact, there were about 4 or 5 different groups at Intel initially who were talking to us individually. And then Intel IT started talking to us and saying that they wanted to offer us a grant. Because what was happening is each local team at Intel was modifying DMTCP in their own special way. And with 5 different modifications, it was becoming difficult to maintain. So it was cheaper for Intel to just pay us and have everything done upstream. So, and I think they knew about 3 of their groups, and we introduced them to 2 more of their groups that were also using our software. But in any case, they've also published about how they use our work in this one article. There's a second, more recent article where they also talk about this. So I'll describe it to you at the level which I can guess at, since it's a need-to-know basis. But at least what I can guess that they're doing, based on the limited facts that I do know, is initially they will do a software circuit simulation of perhaps their next generation CPU. So that might be 1,000,000 times slower. And that's fine. Then they can do their micro benchmarks and make sure that the CPU is locally working correctly. But of course, it's very dangerous to come up with a first silicon unless they test it on real-world software. So if they can use a hardware emulator, and there are these expensive hardware emulators, almost $1 million based on FPGA, then maybe it'll only be 1,000 times slower. And at 1,000 times slower, that's okay, because now we can, for example, boot up Microsoft Windows overnight, or whatever they're testing on. They don't tell me, but I can guess this must be one of them. So the next morning, they then proceed to call up perhaps something from the Office suite, perhaps within the Office suite, a new menu item. And wouldn't it be great if they could only checkpoint after Windows has already been restarted? Then the next time they can do their next test immediately on the next menu item. So this is tricky because now this involves a 3-way collaboration. There is Intel with their proprietary circuit, which we're absolutely not allowed to see. There is the emulator company, for example, Mentor Graphics, Synopsys, and Cadence. Those are the big 3. And then there's us. So we have our open source framework. Even the emulator company has a lot of IP, perhaps 1 million lines of code embedded in their machine, and everything there is proprietary too. So what will happen is Intel will talk to the vendor and explain that we would like to use, that Intel would like to use DMTCP. They would like to extend it as with a plugin to also include this new hardware. Could the vendor please come up with a DMTCP plugin? And luckily for any large machine like that, almost always there will be a way to save machine state and restore machine state. Save hardware, restore hardware. You need that just for your own internal debugging. So ultimately, they're just putting our API as a plugin around their own code for save and restore machine state. So everything is good. And ultimately, we have the Intel circuit, various software used by Intel, the libraries for the emulator at a back end behind the workstation, and us. And then if something breaks, they show us a stack dump and ask if we can figure out what the bug is. Or if necessary, we can have screen sharing. Sometimes there's a new feature that they would need. But it's been a very interesting collaboration. And I can't really say how widely it's used at Intel, but I can say that I've had 2 PhD students now who have done internships at Intel. And also from little bits of conversation, it just seems like they seem to be using it a lot on when they are designing new CPUs before for silicon. But for the rest, I can only guess. I don't know any details. OK, so good. So now we understand the checkpointing. Let's go back to split processes. And let's see how we're going to apply split processes to MPI. So MANA, it stands for MPI agnostic, network agnostic, transparent checkpointing. Initially, we had looked at a different approach, but ultimately we took the current approach that I'll describe here. In the interest of time, I am going to go through some of these slides a little faster now. But I think you'll see the main idea because we've looked at the initial split process slide in great detail. And all of this is just an elaboration on that one slide that we already saw. So what are some features of this? Well, the lower half now is really independent, so we can run on InfiniBand, but we can run on Cray GNI. And that was our initial motivation, because at the NERSC Supercomputer Center, they're using Cray supercomputers. And Cray supercomputers use the Cray GNI network. And when they initially contacted us, my first answer to them is, I'm sorry, but we can't help you because the Cray GNI would take a lot of work to develop a new plugin for that. But eventually, we decided there is a way. And in fact, we got something even bigger than what we ever imagined. For the first time, it is now practical to migrate MPI applications from one cluster to a totally different cluster. And I'll explain why this is actually more interesting than it might seem at first. Whenever you have two different clusters with two slightly different architectures, if you're using any kind of numerical library, you want to tune that numerical library very closely to make sure that it works well with that type of cache, that amount of RAM, and so on. So it's not good enough to just copy the memory image from one cluster to the other if those are heterogeneous. And luckily for us, though, everything on the bottom, the MPI, even the numerical libraries, we're going to stuff that into the lower half. And then when it's time to restart, recall that the idea of restart is we'll start up a trivial application, but we're going to start up that trivial application on the remote cluster. We're not going to start it here. And on that remote cluster, everything has been compiled natively. So everything in the lower half will be running natively with perfect efficiency. It's only the upper half that in principle could be a little slower, but if the numerical library dominates, then we can absorb the small amount of inefficiency from not being closely tuned to the architecture. So here's a basic puzzle. This is something that we found that we could do, and we never imagined when we started in this project. And this is based on something that you would find actually in the paper. So suppose we're running under Cray MPI and InfiniBand. This was the case when we were working with NERSC. So maybe we have 4 cores per node. And when you have 4 cores, there will be an MPI library for each rank, 1 rank on each core in the typical case. And in order to optimize communication, we will use shared memory between any 2 processes. So you can write into the shared memory and the next guy reads from it. Or possibly you might even use this newer API, CMA, cross-memory attach, that allows you even to write directly into the virtual memory of another process. And that's great. That makes things faster, but it really closely ties the 2 MPI processes together if they're on the same host. So we start with 4 on the same host. If we were just copying over memory images, there's no way these 4 would work properly on the new host because now they're separated. But now this will be possible. We can split 4 cores into 2 by 2. We can give up on InfiniBand and switch to TCP/IP, and it just works. Okay, so this is the part where I'll go somewhat faster, but I think if the concepts are clear, then this part is clear, and the rest, if you care, you can just go through the slides again later. Question?
So, is it possible, assuming a virtualization is efficient enough, particularly if you don't share any devices on a hardware device, you have only a single VM, no resource sharing, and that special VM's performance is good enough, very close to native? Can we do the whole system level checkpointing That way, we can avoid a lot of issues because of the layering, because right, you have the application library level, you have the kernel. Is that, I mean, have people explored that direction? Because because that way you have very simple API interface, right? With the OS and the hardware, right? That's just a memory and just the read machine state. That's it. Then move it to another one.
Good. So if I understand the question, it's in practice in HPC, couldn't they use a virtual machine or a VM instead of having the machines run directly under the host operating system? The reason they don't use the virtual machines typically is, one, there can be some overhead when you're using a large amount of RAM, TLB misses, issues like that. Second, you now need bridges to go between, to go across the network. And then third, we talked about when 4 processes are on the same host, we would like to use shared memory or cross-memory attach. That implies that we want to put the 4 processes in a virtual machine on that host. And so if we do that, then if we put all 4 processes in a single virtual machine on that host, we haven't really gained much. We've just added an extra layer of software. The attraction of virtual machines is if we could have 4 virtual machines that are independent. But if we have 4 independent virtual machines, now we cannot anymore use cross-memory attach to write into the virtual memory of a different process that's inside a separate virtual machine. And we cannot have shared memory between 2 virtual machines, at least not easily.
I made the comment because seems like you're targeting some scenario. It's super expensive, super important to make sure I can do a proper checkpoint. And under that scenario, maybe it makes sense to go the actual effort to create a special virtualization such that you get close to native performance, and then now you can have those virtual machines. I mean, dependency on the external world that you don't have control. That one, I mean, it's the same thing, right? You have to solve that anyway. If we disregarding that, can I just do a communication among all the machines such that okay, pass, then just dump everything out? Then you don't care the 4 processes running in the same machine because they just stop at the same time, and then you can then migration everything.
Yeah.
I don't know. Maybe I did something. I don't.
So I've certainly, over the years, I've certainly talked a lot with various MPI developers. So even though it's not my expertise, I can give you my understanding of the situation. Ultimately, there are some codes in HPC which require very low latency. And as part of this very low latency, the MPI may be aware that these 4 processes are on the same host, and therefore they can communicate at almost memory speed.
Yeah.
If these are in separate virtual memories...
Put them in the same host. Why not?
So put them in the same virtual machine?
Yeah, why not? Well, no. Every physical machine has only a single virtual machine, such that I can make sure that virtual machine gets close to native performance because there is no sharing and...
Okay, good. So if you have a single virtual machine for all of this, then it's not clear what you have gained, but you're starting to approach one thing that you do see in HPC. Often they will use containers, not virtual machines, but containers, because containers are, it's not really true, but people will say anyway that containers are like a lightweight virtual machine. And there you'll eliminate some of that overhead. But even 2 or 3% overhead in HPC is really objectionable because these are very expensive machines. So the runtime overhead, they work very hard to reduce it. Yeah, I'm happy to talk more afterwards if you like. But this is my understanding from the people, the experts in the field.
Okay.
Yeah. Okay, so at this point, we have transparency. We don't have to recompile anything. We use the same MPI library. We use the same MPI application binary. It was compiled in the same way as always, MPI-CC. It is the same binary. We're not modifying any binaries, any libraries, nothing. Alas, poor transparency, I knew him, Horatio. And that's the actual quote, although everybody always says, I knew him well. In any case, the idea now is there are previous solutions that have been widely used for checkpointing for HPC, and these are the three most common. OpenMPI itself had their own checkpoint restart service. There's something BLCR from Berkeley Labs checkpoint restart, and our own DMTCP using InfiniBand. And ultimately, it seemed like more and more people were using these solutions less and less. And I'll give you our view of why they are not using the traditional checkpointing solutions. There's an MBYN problem here. There might be M different implementations of MPI. There might be N different interconnects that you can imagine. I really like the last ones. This is for a terminal talking to a mainframe, and this one's for carrier pigeon. But in any case, ultimately, we want to support any MPI working over any interconnect. So it starts to get complicated, and then it gets to become really bad. So I think that's part of the reason. Anytime one piece of the system changes, those old solutions start to break, and then somebody has to go extend them. And whoever was in charge of checkpointing has probably left the job now. And for example, in the case of OpenMPI, there's a famous message on the web where they're saying, as of a few years ago, we have checkpoint restart code. We are looking for somebody who will maintain it. And I think they're still in that position. It's not maintained and therefore not used right now. Okay, so we have, or similarly to show you other examples, BLCR is closely tuned to the actual kernel. If you have a different kernel, BLCR depends on the kernel module, and that has to also be recompiled. And so they only support a limited number of Linux kernels, and that's it. And these days, fewer and fewer, because there's not as much demand for BLCR as there was in the older days. So at this point, we want to achieve agnosticism. I think you know a lot of the story. Maybe I'll just say a little about this one other part that's interesting. So when it's time to checkpoint, we have to put the lower half in some kind of consistent state, or really the upper half in a consistent state. And then we can finally save memory and so on. If we're only using point-to-point communication, MPI send and MPI receive, it's obvious what to do. Just wait until the message arrives at the receive. And since we control the lower half, that's our trivial program. We can add a little bit of extra code to make sure that the message really arrived. But then there are collective communications. A classic example would be MPI broadcast. So one rank is going to broadcast to all of the other ranks. And now there are two cases that we need to worry about. One is there may be some rank which is really, really slow. Maybe we're doing some task-oriented computing, and one of the tasks is taking longer. So at this point, what we would want to do is we would notice that the actual work of the collective communication has not really begun because one of the ranks has not yet arrived at the collective communication. And then the solution should be, well, let's just kill the collective communication. Since no work has been done, nothing has been passed upstairs to the upper half. And so it's safe to just save the upper half as is and tell it to restart the collective on restart. But there is another case. The other case is maybe everybody has arrived. We've begun the MPI broadcast. Some of the ranks have passed the data to the upper half. Other ranks have not yet done it. In this case, it would be wrong to just kill the collective. We need to wait and let all of the ranks catch up and finish the collective communication. But luckily, if some of them have already started, it won't be very long before all of them finish the broadcast. So we need to distinguish these two cases. Do we have one rank that's really slow and nobody else has really started? Or has everybody caught up and some have started to return results? And we have a solution for each one, but we need to know which case we're in. So the solution now is to split our collective into two collective communications. So since this happens by a call down into the lower half, we add a wrapper around the collective communication, which says first do a trivial barrier, MPI barrier, and then do the actual collective communication. And now it's really easy to distinguish. If one rank has never even arrived yet, is very slow, then nobody has exited trivial barrier. If nobody has exited the trivial barrier, we recognize that because, of course, that's part of our code. We'll know when they return from the trivial barrier. So we know it's now safe to kill the collective and restart later. Or else, some of them have already begun in the actual collective. But we know that also because we have the wrapper. We detected that. And that implies that everybody has at least arrived at the trivial barrier. And now we know we can just wait a little longer, and eventually everybody will finish, and it will be consistent. So that was the one little puzzle, an algorithmic puzzle, which finally made everything possible. OK, so then it all works. You've seen this part of the story. This works too. And so now we get the right kind of isolation that we talked about before. Everything in the lower half, as it says, we were going to discard and reinitialize later. Luckily, the network lives in the lower half. If we extend this to numerical computations, we'll put the numerical library in the lower half because we want it to be native on whatever machine we're running. So the upper half will get copied to the new machine. The lower half will get restarted. And because this is a single process, it's OK. All of the data of the application will live in the upper half. And we may pass a pointer to a data buffer from the upper half to the lower half. But the lower half code will operate on the upper half data buffers. So the upper half will stay consistent, and the lower half is independent of the application that we're using. OK, and then this is just a pictorial of what we already know. So we'll go through this quickly. And so we solved the puzzle. It works. So now we can even switch the number of cores per CPU. It's even potentially, if it's an older or newer version of the Intel, which might have additional assembly instructions for higher performance, we'll automatically take advantage of that because everything in the lower half is native. So it's tuned very well. OK, and then we've actually done this on real-world programs to make sure it works. We can usually get very low overhead. There is one issue that we sometimes face, and that's if we have to make many calls to the lower half, perhaps 1,000 per second or more, then in some cases we can see an overhead of about 1.6% runtime overhead. So remember I said 2% or 5% overhead is often unacceptable in HPC because these machines are very expensive. So if we're seeing 1.6% runtime overhead, it starts to make people nervous. So we finally tracked down where that was coming from. And the issue there, it has to do with thread local storage. So we can talk about the details later after the talk. Probably many of you already know this. But when a multi-threaded program uses thread local storage, the way it works is there is a register that points to the beginning of thread local storage, and then each thread local variable is at an offset from that location. And in the case of Intel, that register that is used is the FS register. The FS register essentially points to the beginning of the thread local storage. And then each thread local variable is just an offset from it, and the compiler knows about that and compiles it in the right way. Unfortunately, In user space, you are not allowed to directly change the FS register. It has to go through the kernel. That's a kernel call. About 10 years ago, Intel introduced a new assembly instruction that would allow you to change the FS register directly in user space if the machine is configured or the CPU is configured properly. Over these last 10 years, the Linux kernel still does not support that. But there is a patch. It seems to have been satisfactory in a lot of the testing. Hopefully that will become standard in the mainstream kernel in another year or so. It almost made it this year, but there were complaints that there hadn't been enough testing yet. And then one of the more amusing messages is, I forget the individual, but there was one individual from the kernel developers who was even saying that it's risky to allow users to change the FS register because this involves low-level things about thread local variables, and the users are not as experienced as people in the kernel. And so if we allow users to use this without going through the kernel, they'll probably make a mistake and their software will crash. So we should not allow them to use it. Yes?
What's the motivation behind migrating MPI applications from, let's say, Crane cluster to DCP cluster? Is it just maintenance, or is it...
Good. That's a great question. So the question is, what is the motivation for wanting to do cross-cluster migration from say, Cray to somewhere else? And is it maintenance or something else? So if we're talking about the world as it exists today, people don't need cross-cluster migration at all. Really, we're thinking about future proposals. So what is a big difference between the cloud and HPC? In the cloud, you essentially will migrate your software to an arbitrary machine in the cloud, and maybe they'll do load balancing internally, and they worry about whether all the machines in the cloud are heterogeneous or homogeneous, and they've taken care of those issues. And they don't want to throw away all the machines in the cloud every 2 years and buy a whole new set, so in some sense it'll be heterogeneous. In HPC, the cluster is homogeneous. And so switching to a new cluster in the past was absolutely not an option. And people talk about convergence between the two. Wouldn't it be nice if we had the elasticity of the cloud for people who want to do HPC? So one of the things that back at Northeastern University we're proposing is this would be a nice way, among other things, to make high-end HPC more accessible to computational scientists who have not been running at large scale before, because they can run MPI on their local clusters at the university, and then instead of immediately going on to one of the largest supercomputers in the world and deciding this is the amount of resources we need and here's how we're going to run it, and there's somebody in the help desk there who will help them if they're not sure, there's now an intermediate level. We can give the university an allocation on several of these national supercomputer sites. And now the university can allow a scientist to start running locally at the cluster, and then as the cluster gets busier and busier, now we can use elasticity to burst that local computation out onto a national site. And a scientist can now transparently scale up without even knowing which national site they're running on. So this is one of the visions we have where that might be useful. But aside from that, though, even today, the core reason, the core motivation right now is simply we can now checkpoint and restart just on a homogeneous cluster, and we don't need to worry when they invent a new network. As we said before, it's the MBYN problem. I think I referred to it back here. And that's for a single. This is for a single cluster. We're no longer talking about cluster migration. But on that single cluster, if we want a checkpoint solution that works no matter what that site is using, we would have to do a lot of maintenance if we did it the old-fashioned way. Now we can provide one MANA implementation, and it will run with all MPI implementations, not just the ones that work with us. It will run with all interconnects, and it will be transparent. So that's the immediate motivation right there. And that's where we want to try to finish putting out of business, where was this? I was pressing the wrong button. Got it here. Yeah, there. So these are the three traditional solutions for checkpointing. And as I said, they're being used less and less. Maybe within a department they might still be used, but in our opinion it should be easier to use, and we think that this is the problem that we're solving, so that people can use it also at larger scale without any of these barriers. Okay, so to finish up, yeah, I better finish up very quickly. So at this point, we have this working. What about Windows? Windows uses a process control block. In the process control block, processes are split between user space and kernel space. That's a big problem. If you save the user space memory, then you've now saved a bit of the process information from the last kernel. And so now the idea is if we can tag memory as always upper half and lower half, then it's okay, because now that user space portion of the process table is just lower half memory. And we're never going to save lower half memory anyway. So we don't have to save the process table related information in a Windows process, and we can distinguish the two. So that's work in progress, but we're very hopeful about that. Then I'll try to finish this up real fast, but this is the third strand in what we're trying to weave here. There's the software SimGrid, which I've been also going out on the road trying to sell. It's actually largely centered around France, so I joke that I'm the American sales force for it. But for those of you who've used model checking, in model checking you have the original code, then you build a logical model for it, and then you run that through the model checker to see if the code has bugs in it. And one of the difficulties is you have to translate the code into a logical model. So wouldn't it be great if the code were both the production code and the logical model both at the same time? SimGrid has managed that trick. There are other approaches, but SimGrid has managed it in a very interesting way. The way they do it is all of the memory of the process is a state. And in model checking, we have states and we have state transitions. And a state transition means just run until, in this case, some threads interact and then stop. And now you have a new state. And that state is the state of all the process memory. And in SimGrid, they can recognize where the garbage memory is. If you just did a malloc, they will recognize that's garbage. If you have padding inside your struct between fields, they'll recognize that as garbage. And so they will be able to decide whether you return to exactly the same state. And so we can do things like, this would be the first multi-threaded program I would give my students. So let's do that one. I lost the connection. So that one was MC2 thread. Here's the program, same as before on the slide. Two threads, each one has a variable. If the other variable isn't true, then I'm going to set mine to true. But the bug is maybe both can become true. And if we run, then it does exactly what we said. It will print out soon. Property not valid. Here are the calls down to the library in between. We're actually simulating schedule yield as a lock and unlock. And then down there you see the path. And the path shows you a schedule that will result in that bug. Similarly, mutexes, there's a standard bug that everyone knows about. Thread 1 decides to lock mutex 2 first, and thread 2 decides to lock mutex 1 first. And then when they each try to lock the other one, they reach deadlock. And that works also. And in this case, we had set the depth to 100. So it basically says run thread 1 forever. And then at the right point, I think it's after 1 modulo 4 iterations of thread 1, let thread 2 break in. And of course, we had set the depth to be 100. If we set it to 10, we'll get something more reasonable. And I won't stop to do the third demo, but this involved a lock-free algorithm. So here's the second one, and now we get something easier to analyze, and with a standard logarithmic search, one could reduce it further. We were motivated to get into this because our DMTCP had a bug that lasted for a year and a half. Finally, Intel showed us a program where they were creating 1,000 threads per minute and then killing them. And it showed us a bug that we never knew about before. It was because we're doing a lock-free algorithm, stack-based, to do allocation and deallocation of memory. And we hit on something called the ABA problem, which we had never heard of at that point. And at that point, it was time for us to go to one of our colleagues and start talking about formal verification. And that's where I became a kind of evangelist for more formal verification. And now we have this collaboration with France. And so now it's time to say why that third strand fits in, and then we'll stop. So SimGrid, using a simple new API that I did at Northeastern, we can now detect all these different kinds of cases. I really want to try this out now on undergraduate students next time I teach multi-threaded programming. Undergrads are great guinea pigs that way. And so we have that. It can be done for S-thread. It can be done for MPI. And how do we put everything together? Well, in high-end HPC, they have this joke that they don't debug. What do they mean by they don't debug? Well, debugging, the first idea would be, OK, let's run it under GDB. If you're running with 200 nodes and then you hit a bug, they don't really want you to keep the entire cluster for another hour or two. I'll use GDB to examine what's going on. OK, so if they won't let you use GDB, maybe they'll let you put in print statements. So you put in print statements. OK, this time it was ranks 3, 7, and 14. But next time it's different ranks. OK, let's put in more print statements. We'll do another run and another run. After about 10 or 20 runs, we finally have pinned it down. We know what the bug is. The trouble is the bug doesn't occur until hour number 3. You do 10 runs, 3 hours per run. That's 30 hours. Again, very expensive on these high-end machines. So we want to find a better way to do debugging with MPI or multi-threads. And so the idea now is in SimGrid, they're providing an MPI library that looks exactly like the standard MPI API. And they're providing a POSIX thread library that looks exactly like the standard POSIX thread library. So conceptually, all we want to do is run natively under MPI, then checkpoint, and then restart under this weird kind of MPI called SimGrid. But we will just view it as another kind of MPI. And because I'm out of time, I'll just say that works. And the vision now is to see how far we can take that. Can we really make it possible to debug large MPI codes that have been running for hours? In order to make that vision work, we won't be able to restart 200 MPI ranks in this scheme. But maybe we can guess which are the 3 or 4 MPI ranks that are involved in the bug. So we go back to the previous checkpoint. Maybe this previous checkpoint was 1 minute ago. And we allow only those 3 or 4 ranks to execute forward. And somehow we simulate any messages from the other ranks. And we make a guess which are the right 3 or 4. And then SimGrid says, here's a schedule that gives us the bug. Or if not, we guess for a different 3 or 4 ranks. And we continue until we find the bug. So it's a vision for the future. We're nowhere near it right now, but at least we have a research program that might lead to that. And this is just a pictorial diagram of what we're saying here. Run under native MPI, then switch to SMPI for SimGrid. And you've already been patient, so I'll just say we're applying this now to CUDA. Earlier, we're doing an idea with proxy processes, but now we're combining this as a single process. This becomes the lower half, that becomes the upper half. and that is almost ready to be released. And that should be about it. And let's see. So numerical libraries is the same idea. I really like this question I got one time. This all seems pretty obvious. How come it took us so long to come up with this idea? So this is, of course, my joke answer. Ultimately, though, it's that there are people who know a lot about the Linux kernel. There are people who know a lot about programming abstractions. But there are very few people who work in between and even think about those things, like the link maps and the FS register and the actual kernel API versus the POSIX API, weird things like that. So that's been what makes life a lot of fun for us. And I think I'll stop here. Any questions?
So for the debugging protocols, do you have to rerun the same MPI? Do you have to basically restart on the actual environment, or you can restart on a different environment so that you don't waste the hours on it?
Yeah, the latter of what you said. Sorry, I was saying it fast because I was running out of time, but you're exactly right. We will restart on a much smaller environment, perhaps in the local cluster of that department, and there it's cheap, so therefore we can run for long periods of time while we try to analyze the bug. Yes?
So how often does the HPC or MPI application, when they run, they enable checkpoint? In the other way to ask is,
Yep.
is checkpoint absolutely necessary for MPI, or it's good to have, or important to have? I mean, that kind of scale.
Yeah. So there are different research groups at MPI, and each of them would answer that question differently. So at the very high end, there are software packages that have 10 scientists supporting that code, and the facilities people with expertise on low-level efficiency and so on. And they would say they don't need our checkpointing at all. At another end, there are scientists on their local university machine, and because they don't have so many resources, they want to run for weeks, and they don't believe the machine will stay up for weeks. There are people in the middle who are submitting to batch, and they get a 12-hour time slot, but it's going to take more than 12 hours to finish. They also need our checkpointing. And then there was an interesting proposal that we heard from Argonne National Research Lab. They're building Aurora, which will go live in 2021. And this will probably be the largest supercomputer in the world. And there, they have this request from the Department of Energy for on-demand computing. And they had to explain it to me. At first, I didn't quite understand what they meant by on-demand computing. What they meant here is that when you have the largest supercomputer in the world, you don't want to run 100 medium jobs. And so they'll tell people, if you have a medium job that can run on another cluster, do it. We don't want your job here. This is a precious resource only for the very largest jobs. But that means that a typical job is going to be using a lot, maybe most, of that supercomputer. And then there are the experimental people who have large physical experiments, hundreds of millions of dollars maybe, in physics, in chemistry. They set up for their experiment, and then there's the problem of data acquisition. In the past, one computer could do the data acquisition. Then a small cluster could do the data acquisition. And then with Moore's law, the experiment generated data faster, but Moore's law could sort of keep up. We had more and more cores. Now Moore's law is dying. So now that cluster can no longer keep up. So they have to go to an even larger cluster. And some of these experiments are so large that they really want to use a supercomputer for the analysis. They could afford to, say, throw out 95% of the data and use a smaller cluster. But if they can analyze all the data, that's much better. And they do not want to have their huge $100 million experiment be put in a batch queue and then be told when you get to the front of the batch queue, that's when your physical experiment can start. So at this point, the DOE is saying, if you have a big job running and you get the notice that this physical experiment is going to start up, you will kill that batch job or else maybe you can checkpoint. And so finally, we're hoping for our big chance, like in Hollywood, to get on the stage and see if our method can work. So we still have a year to go, and I don't know, but we're going to give it a try anyway. Yep. Good. Other questions? Thank you.
Thank you.